Recall when studying dy dx is equal to y, which was a differential equation of the form y prime equals y, we initially guessed that the solution y equals c e to the x. Suppose that we weren't able to just guess this general solution c e to the x. What if we had to find it? So the question is there a technique? Is there some technique that we can use in general to do this, to find general solutions? And the answer is not always, but sometimes there is. And in this course, we're going to look at a couple different techniques for doing that. So one technique is called separation of variables. So a key and important technique, and the first technique that most people learn is called separation of variables. And by that, we typically mean that we separate the two variables into two functions that are being multiplied together. So for example, we may have a differential equation of the form dy dx is equal to fx times gy. So what we've done here is we've separated out the two functions into variables, all in terms of x and all in terms of y, being multiplied together. And then what we do is we solve for dy equals f of x times g of y times dx, effectively treating these two things as a fraction, multiplying this to the right-hand side, and then we divide by this g of y function. So we get 1 over g of y times dy is equal to f of x times dx. And then our last step will be to integrate on both sides both of these two. So we integrate 1 over g of y dy, and we integrate f of x dx, this with respect to y, and this with respect to x. How do we do that? We do each problem by calculus. So here we'll solve this problem by calculus, and we'll solve this problem independently also by calculus. Okay, so we have this little bit of theory here, which we're calling separation of variables. If we have a differential equation in this form, then we can write it in this form, and somehow that will allow us to solve the problem to find general solutions. Okie day. Look, nothing tells the story like an example. Let that be your mantra in mathematics. Nothing tells the story like an example. Theory, while dense and compact, containing a lot of information in just a few strokes of the pen, is difficult to understand. Let's look at an example. Nothing tells the story like a good example. How can we use separation of variables to solve this differential equation? Well, we're going to go through this process. Currently, this problem is in a form similar to this. Now we need to put all the y's on one side and all the x's on the other. So let's do that. This becomes dy equals to y times dx. Then we bring this y to this side. So this becomes 1 over y dy equals dx. Now we integrate on both sides and we solve using calculus. What is the integral of 1 over y dy? So the integral of 1 over y dy equals the integral of dx. To solve this problem, this is now the natural log of the absolute value of y plus a constant. Meanwhile, the integral dx is just equal to x plus another constant. This is a constant c1, this is a constant c2. We can rewrite this overall with one constant by combining the two constants. So let's say x plus c3, where here this c3 can be thought of as c2 minus c1. Now I have one constant of integration overall for this problem. How do I find x by itself? Raise both sides to the power e. E ln, absolute value of y, equals e x plus c3. This, with the exponent, becomes e to the x times e to the c3. You will recall that x to the a plus b is x to the a times x to the b. an exponent rule from algebra. Then here, this becomes y, because e and ln are inverses, is equal to e to the x times e c3, which is just another constant, for some constant c. Okay, so now we have y equals c, e to the x for some constant c is the general solution. And so what we've done is we have used calculus to solve this problem to find the general solution. Just to recap what we did there, we started with a differential equation. Okay, this is a separable differential equation. We separated the variables. So we separate the variables and solve by integration. Then we get a general solution. And this general solution should be a solution to this problem. We can, in fact, at this point, verify that our solution is actually a solution to the original differential equation, since y prime is equal to the derivative of c e to the x, which is equal to c e to the x is equal to y. And so we can verify that, in fact, our general solution indeed solves this differential equation. One should also observe that the constants of integration lead to the constant in the general solution. And when we find a particular solution, what we're effectively doing is specifying uniquely the constant of integration. So this constant that emerges in the general solution actually comes from the constants of integration from solving the calculus problem.